In discussing the nuclear fusion inside the sun, remember one of the early steps was that we had the two protons come together to make a deuterium nucleus, positron goes spewing out, but the other thing was a neutrino was produced. And the neutrino is one of these things here that is a subatomic particle and was really sort of figured out that it existed because the equations did not balance energetically prior to including that into the equation. And so subatomic physicists started to realize there's this small particle, very, very low mass, because the masses were working out in the equation just fine. So this thing had to have such a tiny little mass, it was below the ability to measure. And then they realized that it had to have some energy. But it also had to be something that was electrically neutral. So they call it neutrino, like little neutron. It was a particle that didn't interact with very much. In physics, we have the strong force, the strong nuclear force is what's kind of holding the nucleus together, and something called the weak force. The weak force is part of what's interacting with neutrons, kind of like holding them together. A weak force is what works with the neutrinos, and gravity. Those are the only two forces it interacts with. It does not interact with the strong force, does not interact with electromagnetic force, which is electrically neutral, so it doesn't do electromagnetic. It's very little interaction, even with the weak force and gravitational force. And so neutrinos barely interact with anything at all. And the speculation is that with the trillions of neutrinos going through every square inch of your body every second, they just go in, they go out, they don't do anything, they just go pass right through, they go pass right through the Earth. I mean, even at nighttime, you got trillions of neutrinos going through every square inch of your body coming through the Earth because they don't interact with anything. It would take several light years worth of lead shielding to block a beam of neutrinos. They just don't interact with things. And so, I mean, for you, that's good. They go in, they go out, they don't do anything. It's like radio waves. They go in one side, out the other side, they don't do anything. What you don't want is for something to go like halfway in or interact as it goes in. And so neutrinos typically don't do that. And I say typically. The occasional neutrino will, every few years, a neutrino will probably hit an atom in your eye and bounce off of it and cause the atom to release a little bit of energy that makes a little photon of light. And you would see that if you were in a perfectly dark room, there'd be one photon of light, one particle of light produced. Now, normally you would never notice that because that one particle of light is completely overwhelmed by all the other light that's going in your eye, so you'd never notice that there's that one little extra particle. And so completely lost in all the background. These things are tiny bit interacting, and so they are barely detectable. Physicists have discovered there's three different types of neutrinos. There's the electron neutrino. That's the kind of neutrino that's produced when you make an electron or positron, okay? And so that's what's happening with coming out, being produced inside the sun. There's also a tau neutrino and a muon neutrino. A muon or mu particle is a subatomic particle composed of just a couple of quarks. They move around inside of the nuclei also. Tau particle, another subatomic particle. Again, beyond the level of this class, going into the details as to how all that works. But there's three different types of neutrinos. Only this one type is produced inside the sun. Now, each of these neutrinos interacts with different kinds of materials. So if you're looking for solar neutrinos, it kind of would make sense that you would go for the one here that's being produced. So that was what was done. Raymond Davis, astrophysicist here, and his graduate students were working on a project to detect solar neutrinos, and they used an old salt mine, the Homestake mine, deep underground, because they didn't want stray other particles hitting their experiment. They wanted to be completely shielded against cosmic rays or anything else that might make any kind of impact on the experiment. And so this is deep underground, and gives you an idea as to how big this container of chemicals is, because you can see in the picture, you know, people. Okay, this giant container perchloroethane. This is basically like an industrial sort of cleaning solution, and deep underground. But neutrinos don't really care about the ground, so neutrinos are just continually going straight through the earth and going through the container. And theoretically, what would happen is that every week or so, you would be able to produce maybe a dozen argon atoms, because the chlorine would interact with the neutrinos now and then, and you'd maybe make a dozen argon atoms. And so the idea would be the graduate student's job is to find them. Okay, well, it turns out that argon is a noble gas, doesn't interact with anything else, would float to the top. There are ways of doing this. It was right at the limit of the technology of what was available in the day that they were doing this, but it was possible. Okay, and so the idea was to measure the exact, you know, this, and then that would verify the theory about solar nuclear fusion. Because they had several ideas about what was going on inside the sun. And they wanted to verify this, and as I said before, there's more than one type of nuclear fusion possible, of hydrogen fusion, and it's believed that a certain percentage is the actual proton-proton chain I just told you. A couple other types of proton-proton chain or subchains are possible, and we calculated the different percentage of each, and so we wanted to measure this and make sure. Okay, problem. They were only finding 1/3 of the neutrinos that they were expecting. Okay, so first thing is, well, maybe the experiment was badly designed, so they worked through. No, that seemed to work. Maybe the graduate students weren't doing a careful enough job finding the neutrinos. No, that wasn't the problem either. So what was going on? Several possibilities. One is the core oscillates. Now remember, the core actually has a sort of built-in thermostat, and that is that if the core is fusing too fast, in other words, if it's too hot and too high pressure and fusing too fast, then what happens is the outward energy, the energy is being released too much, and it expands and cools off. Now, if it expands and cools off, that means it slows down the rate of fusion until it stabilizes. If it's too big and fusing too slow, then then that means the gravity is squeezing it more than the energy is pushing out, and so it compresses, it shrinks, and gets hotter, and that speeds up the fusion rate. And so one possibility is that they were thinking maybe that the core is doing this sort of weird thing, and the core is too small, and too small, and it speeds up, and now it's too big, and it shrinks, and it's too small, and it speeds up, and it's too big. So what happens is it alternates between being too big and too small. And so we just happened to catch it when it was on the big cycle and slowing down. And so, well, if that were the case, all you'd have to do is wait for a little while, and the core would be getting smaller and speeding up, and would get more neutrinos. That's not what happened. We ended up not getting more neutrinos. And so that idea was not what was going on. The other idea they came up with is maybe there's some other kind of particle that's very, very weakly interacting, which is why we've never seen it before, and it's interfering with the nuclear fusion, maybe making the fusion run slower than we thought it should be running to produce the right amount of energy in the sun, or maybe it's interacting with the neutrinos or something. So and they call them weakly interacting massive particles, WIMPs for short. And so the weakly interacting massive particles, they have the enormous effort searching for additional subatomic particles that had mass and were weakly interacting. That there were several characteristics it had to have in order to have the effect of masking the neutrinos. Nope. So that's not it. So that means they ruled out oscillating core. They ruled out that, and the only thing that really made sense was neutrinos are weird. And so they said, well, we need to do more studies. In a couple big studies here in Canada, at the Sudbury mine, deep underground, they had a detector, and the Kamiokande, which was in Japan. And the way the Kamiokande worked was you had this entire reservoir filled with water, and the neutrinos would come in, hit the water, cause a flash of light, and they had all these detectors around here. And so here's a boat and some technicians changing out the detector. In the Sudbury mine, you had actually the container of purified water inside another container of different kind of water. You know, some of this water was regular water, some of the water was made of heavy water, so deuterium oxide, and as the neutrinos come through, they'd interact with all this. What it would do is interact with some of the neutrinos would interact with one component, some with another. The Sudbury mine was actually sensitive to all three types of neutrinos, whereas the other detectors were only looking at electron neutrinos because that's all we expected to find coming from the sun. And what happened was a couple of things. First of all, they built an even bigger Kamiokande called the Super Kamiokande, and both the Kamiokande and the Super Kamiokande were detecting only 1/3 of the neutrinos expected. And that was a complete shock to them. But the Super Kamiokande did one other thing, though. It was able to show that the neutrinos going, because they were using a nuclear reactor in Japan to produce the neutrinos, and it would go through both the Kamiokande and the Super Kamiokande, you know, one of them just a fraction of a second later. But the percentage was slightly different going to the second one. And so that led them to suspect that maybe the neutrinos were actually changing from one type to the other type in that fraction of a second. Well, it takes 8 minutes for light to get from the sun to the Earth. Neutrinos travel almost the speed of light, so they take just over 8 minutes to get here. And if they can change a little bit in a few seconds, by 8 minutes they would have changed a lot, which means that if neutrinos can change from one type to the other, they would have had plenty of time to change from electron neutrinos to either muon or tau neutrinos and back again, and then to the other kind, and so forth. And so in that time frame, what would happen is by the time they got to Earth, that what used to be all electron neutrinos would be split evenly between the three different types. And so if you're just looking at electron neutrinos, you only get 1/3 of what you expected. But you should get the same number of muon neutrinos and tau neutrinos. And that is exactly what they found when they looked at the Sudbury detector, which was able to find all three. And so that means that neutrinos do have this tiny little bit of mass. It's not much. Electrons don't have much mass, but these things have somewhere, you know, in the order of like 4/1,000,000ths of the mass of an electron. So that's hardly any mass at all, but they do oscillate between all three different types. And so that means that's why the early detectors, not just the Homestake mine, but all the early detectors, kept consistently only finding 1/3 of the neutrinos. And that's because they were only looking at one type. And once you start looking at all different types, you find that, oh, wait, they are all there. It's just that